Hi, everyone. Thank you so much for tuning in. This is our second virtual, sorry. This is our second virtual event. Today we have a speaker from IBM, and he's going to talk about unfair bias in machine learning. As an introduction, I will have Tim from IBM to give us an intro of their Coursera course.
Hey guys, can you hear me okay? Can you hear me okay? Okay, great. So my name is Tim. I work with the IBM data science community team. We're normally based out of San Francisco, but of course, right now, all working from home. And we're a fast-growing digital space for data scientists, AI developers, machine learning engineers, essentially a place for data scientists by data scientists. We offer lots of learning resources and great content, and access to a fair number of our IBM experts. So definitely check us out. If you sign up, you get a 1 month complimentary access to select IBM courses on Coursera right now. And with that, thanks for joining, everyone. Hope you have a good time and enjoy the talk.
Ooh, I'm on. Okay. Hello, everyone. I'm hoping people can hear me. Tim, can you put a little a comment in the chat? Perfect. Thank you so much. So this is interesting. I don't know who's attending or how many people are attending, but I'm hoping there's somebody out there listening to me. So hi, everyone. My name is Okar Litter. I work for IBM. I'm a developer advocate right now. And I put my Twitter handle at the bottom of the screen, as you can see, as well as another link. That's where I usually hang out and give talks as well. So feel free to check that out. Today, our topic is removing unfair bias in machine learning. And I was thinking about this title, removing unfair bias. I guess unfair bias to one party or individual is fair bias to somebody else. And we'll get into some of that, of course, today. But just talking about theory of, what is bias, how does it show up, etc. is good. But also, I want to show you a toolkit that you can use to actually detect bias in data. Also, use it to create machine learning models that mitigate some of these biases. All right, with that, let's get started. I know we have about an hour. My talk's maybe 45 minutes, so I'll keep an eye on the question sections. If you have any questions, please let me know. But also, I'll remind you at the end. By the way, the slides are available. I'll share the link later as well. All right, so here's the agenda for today. First of all, hopefully everybody's keeping safe and doing well. And for us, I live in San Francisco, and we are still in a semi-lockdown now. And I'm really getting used to working from home. I'm quite an introvert to begin with, so this suits me just fine. But hopefully everybody's keeping safe and keeping themselves entertained. So the agenda today, we'll talk about introduction to fairness. What does it mean? We'll look at some of the technical definitions that have come out of academia. Along with the metrics, we'll look at some of the algorithms you can use to not only detect bias, but also mitigate bias. I'll give you some guidelines on when to use what metric. You'll see there are tons of metrics, so it's kind of hard to just remember them off the top of your head, and that's fine. Then we'll go into an interactive demo. This is where I want to show you the toolkit, the open source bias detection toolkit that IBM is a big part of, but it's definitely a community effort, and it's called AI Fairness 360. I'll give you some links as well. And then we'll go through a notebook really quickly and a UI demo. Okay. So I think this is a question that shouldn't even be asked, but it's a necessity, right? So why do we care about fairness? In my mind, we care about fairness because we all want to be treated equally. Now, we know that human decision making is flawed in many ways and is shaped by our experiences and what we have in our memories, right? And subconsciously, I think bias. There's always a bias in our heads, and it, like I said, it may not, it may be below the surface, but it definitely is there. I personally feel bias is a way sometimes to take shortcuts, right? So based on my past experiences, I may have certain perceptions about certain things in life. Now, everybody assumed that we're moving on from a world where humans make all of the decisions with the limited knowledge they have, to a world where machines are making a lot of decisions for us. And the idea or the hope was that since machines don't have emotions, maybe the bias will go down. Actually, evidence has shown that what we're doing by transferring all of this decision making to machines is compounding our bias, right? So whereas previously human beings were making these decisions one at a time at a slower pace, now we're making the same decisions about our jobs, about who should get a loan and who should not get a loan. We're making these decisions through computers, through machines, a lot faster and a lot bigger scale. So in fact, we are compounding this bias, and that's why it's really important to catch these at an early stage. If we were to talk about defining fairness, there's a really good paper and a YouTube video talk, and I'll share the link of that as well, by Narayanan in 2018, and he discusses 21 mathematical definitions of fairness. I guess it's a good thing that since it's such a complicated topic, it's good to have more definitions than less to cover a variety of issues. But also, he shows mathematically how a lot of these definitions actually conflict with each other. And so it's really hard to get a completely fair model that satisfies all of these 21 definitions. That being said, I think one takeaway from the talk today would be there is no one-size-fits-all definition. And so you really have to be cognizant of the context. You have to be aware of the different stakeholders involved, and then one metric or the other may fit the situation better than the others. And the way you define fairness really impacts bias and what that means. So for example, in 2008, there were two researchers who did a study on Google Images, right? So they looked for the word CEO in Google Images, and at the time, only 11% of all the images that showed up on the first page in Google Ranks showed women. But in reality, at the time, there were 27% of US CEOs, or CEOs in the US were women. And so in this case, how do you determine a fair percentage to show there? 11% definitely does not seem fair to show on the first page. Should the algorithm show 27% because that happened to be the case, as biased as that may be? Or should it show 50% because 50% of the population is women? And so again, depending on where you come from, what your experience is, it's important to even before you start looking at bias, have a discussion around what you consider as bias and what other stakeholders in the project may consider as bias. So here's an example. People have probably seen this before. This was an article in ProPublica. There's an algorithm called Compass, which was used to predict whether prisoners in Florida are more likely to commit another crime if they were released on parole. And this was later investigated and found that Compass algorithm incorrectly labeled African-American defendants as high risk. Not only that, it did that as at twice the rate it mislabeled white defendants. So that obviously there seems to be a bias there. What you don't hear often is that Compass actually tried to eliminate gender and racial bias from the start. So when they were testing their system, they went for something called a predictive parity. And so they were looking at unfavorable outcomes for both the Black defendants and white defendants. And ProPublica paper, which again I'll link to in my GitHub, shows that was not a good metric to use. So even though by that metric, their algorithm, the Compass algorithm, was seemingly fair, but if you look at another metric of fairness, like if you look at false positive and try to balance that, then it quickly became clear that the Compass program was actually very unfair, and there was a lot of bias against African American defendants. Now again, I show this chart, and sometimes I zip through this in a minute. So I just want to be aware that of course there's more context to this, to these two cases and what happened. So I'm by no means taking that lightly. The other thing I want to quickly mention is when we define bias, we say it's a systematic bias against a community, a group, or an individual. So this study was done not only just in this one case, but they looked at a vast number of cases, and then came to the conclusion that in majority of them the software was biased. I'm going to quickly check for questions at this point. All right, there's people joining from all over the world. That's amazing. Welcome, everyone. All right, let's move on. So this is just one example, right? Here's another example. So Amazon had this AI recruiting tool. I should really date this article. The date is missing on it. I'm sorry for that. I'll edit the slides to put in the reference and the date. But essentially, the recruiting tool, it was the first level of filter, right? So new people are applying to work at Amazon, and this tool would look at their resume and make a decision if that should go to the second tier in the recruitment process or not. The problem was the model that they used was trained in over 10 years on resumes that were primarily submitted by male applicants. Right, so the model really didn't have an idea if somebody who's not a male would make for a good candidate or not, and so it was automatically penalizing things like if the resume had anything about a women's chess club captain, or playing for the women's soccer team as a hobby, then that resume would not get as many points as the typical activities that probably men are involved with. In this case, Amazon did try to remove this bias, but it was so inherent and complex in the model itself that they ended up scraping this tool. Now, here's a more recent example. This one should have a date. So this is 2019, last year, end of the year. I came across this tweet by DHH. He's the creator of Ruby on Rails, as probably some of you know. And the situation here is that him and his wife, they have joint property. So technically on paper, they are equally wealthy, and they applied for an Apple card. And it turns out he got 20x more credit limit than she did. And he tried to contact Apple. He tried to contact whoever the credit company was that was doing the modeling on behalf of Apple. And he got through to support, and it was funny. Funny in a way, the support person did not know why the model behaved the way it did, right? So there seems to be some bias in here, and the other part of the coin is explainability, and it was very hard in this case for the support person to explain why the model did what it did. And at the bottom, you can see Steve Wozniak also complaining about that Apple card, right? Again, this is a very new case, and based on the popularity of people who have raised this question, Apple immediately took some actions, and they were last I saw they were investigating this issue to see what's going on. But just to give an example of different kinds of or biases that can exist in different situations. Okay, one more time, check for questions. There's nothing. Okay, so here's our toolkit, right? So we understand what fairness is. We kind of understand what bias is. We haven't really looked at the metrics. That'll come shortly. But this AI Fairness 360 toolkit is completely open source. It's an effort led by IBM, academia, and also it's like I said, it's on GitHub, so anybody can participate. Last I checked, it has over 75 metrics of what fairness is. It gives you good guidance. There's a whole section that guides you on when to use what kind of fairness mitigation algorithm and metric. Plus, it's got industrial use cases, which is helpful if you're looking for medical versus financial sector. The framework itself used to be Python only, so there's a pip package that you can install and work with it. But also recently, very recently, maybe about a month or so ago, they released a package for R. So if you're a data scientist who works with R, now you have an opportunity, or you have a chance to use this toolkit with R models as well. Okay, and again, I just want to say this is completely open source. It's not an IBM only thing, but a lot of universities, academia, researchers work with IBMers to enhance this toolkit. Okay, so what is this bias thing we keep talking about? We've looked at some examples, but mathematically, how do you define bias, and where does it come from? Right, the second part. If you look at the second part first, where does it come from? It comes from us. It could come from decisions we have made in the past. So there's a lot of historical context there. A lot of times, bias comes into your data from the way you do your surveys or the way you collect information. If a common example is, if you're doing surveys and two different people are doing surveys, they'll have their own intrinsic biases that'll show up in the data that they are collecting. So that being said, here's an example. So this was a study done by MIT of top facial recognition services. And it turns out most of them were very good at detecting faces of light-skinned males. In fact, 99% accuracy, versus only 65% accuracies for detecting dark-skinned females. Right. So what's going on here? They did some research. A common cause of introducing bias in your algorithms is either oversampling or undersampling your data. So in oversampling, you have your two classes, the blue one and the orange one, and you don't have enough data for your orange class, and so you start replicating or duplicating that data to make it look like there's enough data to compare with the blue class. And in undersampling, it's going the other way around. So you decrease or you subsample your data from the blue class so that the amount of data is comparable to the orange class. And the problem there, of course, is, when you're doing your sampling, you have to make sure, or the question to ask is, are you really taking a sample that is representative of the complete blue data set? Okay, I'm going to check for questions one more time. No questions yet. Okay. All right, hopefully, I know this is pretty introductory, but hopefully it's making sense. Another question people ask is, or a suggestion is, well, seems like age is a big thing, right? So when you're looking for a credit card or a loan, if you're under 25, good luck. And so people say, okay, so age seems to be a problematic attribute. Let's remove that altogether. And there are other attributes like that, right? So maybe there's bias based on gender, maybe there's bias based on race. Let's remove those attributes. The problem there is a lot of times there are proxy attributes or attributes or hidden attributes that correlate very well with your protected attribute, we call them. And so even if you remove the protected attribute, the bias still shows up in the proxy attributes. And this is a very good example. This is a map of Brooklyn, New York from 1977, where banks use something called redlining to discriminate potential customers by zip code. Right? So even though in this case they're not doing it by race, the zip code correlated really well with where groups of people lived. And so they were providing different amounts of credit to areas depending on ethnicities, even though they claimed they're not biased. In fact, this was so popular back in the day, like redlining by itself is, you'll read that term in different papers, and what it means is using proxy attributes to discriminate, instead of doing it directly with the protected attributes. So here are some fairness terms that you need to know in order to use AI Fairness 360 Toolkit. But in general, too, I think if you read papers, if you use toolkits by other companies or other open source ones, you'll come across these terms, right? So protected attribute is the attribute that may be used to bias against certain group. So an example being race, gender, caste, religion, right? And then privileged group versus unprivileged group. So privileged is the group that is getting an advantage, and unprivileged is that is at a disadvantage because of the bias. The privileged protected attribute is the protected attribute value that has historically seen systematic advantage, right? So in the case of the credit card, where DHH is complaining, the privileged protected attribute may be male, right? So historically in that industry, and this is sort of a guess on my part, there's a disadvantage for females. Then you have group fairness versus individual fairness. So group fairness is where you want different groups to have equal, to have a playing level field. And then individual fairness, again, that is if individuals are similar and you run them through an algorithm or a model, then the outcomes should be similar for those two individuals, regardless of what race they belong to, what gender they are, what caste, etc., or what their age is. Fairness metric is the measure of unwanted bias, and I'll show you a couple of what these metrics look like. And of course, favorable label is a label whose value corresponds to an outcome that is an advantage to the recipient. So again, some examples for you here. So the first metric is statistical parity difference. So this is fairly easy to understand. So the way to read this picture is there are 10 individuals in the first group, which is the unprivileged group, and there are 10 individuals in the second group, which is the privileged group. And in this case, after running through the model, favorable outcome was given to 6 out of the 10 in the first group and 7 out of the 10 in the second group. And so we can say that the first group has a bias against it, and this is a simple example of just subtracting the ratios and getting to 70 minus 60, 10%. So there's very easy metric to understand, and this is the one that Compass was using to state that their algorithm is completely fair, because they were getting this predictive parity as close to 0 as possible. Disparate impact is, excuse me, it's very similar to statistical parity difference, but instead of doing a difference, you're doing a ratio. That's the only difference here. Then there's a different one, right? So equal opportunity difference. Now you're looking at the true positive rates, and not just at all the favorable outcomes, right? So in this case, if you see, there are 5. 1, 2, 3, 4, 5. Yeah, there are 5 that are positive, true positive, and then there are 2 that are false negative. That the truth is that they should have been positive, versus in the second group where you're looking at 6 versus 1, or 6 out of the total 7. In this case, 5 out of the total 7. So you see that it's the same situation between the two groups, or between these two cases, but your statistical parity difference is -10 versus equal opportunity is -15. And again, depending on the context, one may be better in the situation than others. In fact, what AI Fairness 360 suggests is you run through a whole bunch of these metrics and see which ones are completely off and take a closer look at that. Yeah, by the way, AI Fairness 360, and I don't think there's any toolkit that will, you give it a data set and it magically comes back with, oh, here's your bias and here's how you fix it. Instead, what it does is that it comes back, you tell it what kind of bias you're looking for, and you can look for multiple biases, and it comes back with multiple numbers. Just like your model, a machine learning model perhaps comes back with a confidence score usually, and not a yes or no answer. So again, there's some guidance on what kind of metric you should use in certain situations. but you have to keep in context the different stakeholders and basically what's at stake. Now, within group fairness, there are two different worldviews again. So if I were to ask a question, do SAT scores correctly predict the abilities of the applicants? One worldview is what you see is what you get, which essentially is saying, yes, SAT scores correlate well with future success and correctly compare the abilities of the applicants. If that is your worldview, you look at certain metrics, just like we saw before. If your worldview is we are all equal, then you're saying that actually SAT score may contain structural biases, and so it's its distribution across these different groups may be different. So it's not fair to compare a kid who's coming from a non-English speaking parents to maybe another person who's coming from parents who speak English at home, versus single parents, right? So versus low income, this is what the structural bias is. And so if you're looking at that kind of, if that's your worldview of the SAT score, then you look at disparate impact or statistical parity difference. Now, again, like I said, there's 75 and more of these metrics, and it's really easy to get confused. So I'll show you with this toolkit at least how to look at definitions. All right, quick check on questions. Oh, Alan's here. Hey, Alan, thank you. I see some familiar names. It's awesome. Okay, so here's another way to look at it, right? So as you know, this typical machine learning lifecycle, right? So you have your data, you look at your data, you do some data analysis, cool kids say data wrangling, whatever that may be, and then you come up with your models, you score it, and you do all of your testing evaluation, and then you deploy it, and so on. With bias, a lot of people ask, like, where should I test for bias? And with AI Fairness 360 Toolkit, there are essentially 3 places you can test. So the first one is with your data itself. Okay, excuse me. So you can have a bias metric on your data itself, and based on what you find there, maybe if you do detect some sort of bias, you can use some pre-processing algorithms to try and massage your data in a way so it's fair to all groups. If not, you go through your standard pre-processing. The second place to introduce bias detection and mitigation might be in the processing itself, might be in the model itself. So that's called in-processing versus pre-processing. So this is where you use the models that are in the AI Fairness Toolkit in order to decrease bias while the model is being trained. Okay, and the last one is your post-processing. That's where you already got a model, and at this point, you can still detect if there is a bias or not. But now you may be changing your target classes or your labels that come out of the model based on certain algorithms that I'll show you in a bit. As you can probably imagine, it's easiest and most makes more sense, and it's easy to understand the mitigation process and the metrics that come out of the data itself versus what's going on in processing and post-processing. A lot of times, this is sort of decided for you. And what I mean by that is you may not actually have access to the data, to the underlying data that was used to build the model. If you do, that's good. That's great. Then you can do your pre-processing metric detection or bias detection plus pre-processing algorithm. If you don't, if you get the data and they say, no, you cannot touch the data, you can't even see the data, it's kind of strange. But if that's the case, then OK, then you can do some in-processing perhaps. But a lot of times we get these models that are completely black boxes, right? Complete black boxes. And so you may get this, this model, somebody wrote it in scikit-learn or whatever, and now you have this model. OK, what do you still want to be able to detect if there is any inherent bias in the model and be able to mitigate some of that post-process. So a lot of times, based on what access you have and how easy it is for you to get hold of the data versus model, you can inject your bias techniques or bias mitigation techniques at the right level. Here are some of the algorithms. So by the way, each one of these models or algorithms comes with a very detailed paper, or most of them do. And right now, I'm in the process. I'm by no means an expert in every one of these. So I'm going through a lot of these papers and trying to understand what is happening sort of behind the scenes. So you should do the same. In pre-processing, reweighing is a little bit easier to understand. So that's where you're modifying the weights that you give to the different features in your training data set in order to get a better result or a less biased result, right? And let me show you. Let me show you some of these papers, right? So again, as I said before, a lot of these papers are coming from outside of IBM. Actually, a lot of these are coming from academia, and then together with IBM researchers, they implement these models into AI Fairness 360. So I'm actually reading the reweighing paper. I was reading it yesterday as well. This is very interesting read if you're into that sort of thing. I think it's important, right? So I think there's one thing is just using this this toolkit or any other toolkit blindly, but I love the amount of transparency they've provided here. You can actually go and read the background on where where the algorithm came from and then how it was implemented, especially since AI Fairness 360 is completely open source. So here's a little bit of insights into the different processing algorithms. So in reweighing, you're changing the weights, as I said. A lot of classification algorithms or models, like if you look at scikit-learn, which one did I look at? I think I looked at the decision tree or something, and it takes in the weights as one of the parameters. And so in this case, you would use something like reweighing to figure out what those weights are for the different features, and then pass that into an existing scikit-learn model, perhaps, right? So in pre-processing, you can do three things. The first is you can change the. First thing is you can just ignore. You can just ignore the protected attribute and any proxies. And the research paper that I was reading on reweighing proves that that is not a very good strategy and doesn't really help. The second thing you can do is subsampling. So you can subsample. You don't have to use all of your training data. You can subsample data in a way that you reduce bias for certain privileged or underprivileged groups. And the third thing you can do is attach weights to different features so that you get a more plain level field. Again, go through that paper. It has a lot more information that I'm giving here. And you can see in all of these cases, either your input space is being modified or your weights are being changed. And so all of this happens pre-process. There's also a big debate on bias versus accuracy. As data scientists and as managers and business decision makers, I think we are so focused on accuracy. We are always aiming for the best accurate model that I can ever get to, right? That's what Kaggle's all about sometimes. And that comes at a cost. That comes at a cost in the sense that the more you increase that accuracy, try and increase that accuracy, the more you're ignoring bias. So one way to look at it is right, like how much should you when you're reducing your bias, when you're reducing your bias, you're also reducing your accuracy. And so there's there's definitely some give and take here. And so there might, so in order to decide thresholds where you're kind of balancing your accuracy and fairness, you need to do that. And I think one of the slides shows a chart where the accuracy crosses your biases coming down, and that's where how do you know where to pick that threshold? And that's a very business problem, right? You look at the legal issues, you look at ethical issues, you also have to look at trust issues, right? So you might be losing your client's trust or customer's trust if later on it is found that your algorithm or your model or your product has an inherent bias in it. But anyways, there's definitely a tug of war going on between bias and accuracy. With all that being said, preventing bias is hard, as you can imagine, right? Actually, a lot of us, I feel, especially if you're new to data science, And I don't have a background on people who are attending, but if you are new to data science, I don't think this is taught, right? This is in the courses that I've taken on Coursera or even otherwise. This is usually skipped, and this is an important thing, especially the times we live in. And like I was giving this webinar last time, and somebody was complaining that I didn't spend enough time in discussing what's going on in the country right now, or even like, where does this bias come from, or who's it at a disadvantage. But like, all I can say is this: it's not just an American problem. I grew up in India, and I know there's a lot of bias going on there as well. So it's everywhere. But as software developers and data scientists, this is one of the tools we have to make, maybe not even make a difference, but at least raise awareness with the tools we work with. So the first tip here is work with your stakeholders early to define fairness. A lot of times, as we saw with the Google images, what is fairness? What do you consider fairness? And that changes depending on who you ask and what their interest is in the solution or product they're building. The second tip is apply the earliest mitigation in the pipeline that you have permission to apply, right? So with the data, it's slightly, at least for me, it's easier to understand the different metrics and also what kind of mitigation algorithms you can apply, versus in processing, where you're now fiddling with the actual, the actual model or the actual training. An example of that they have in the paper is you try and penalize the loss function more for protected attributes than for other attributes. And you can see that's getting a little complicated, which is fine. If you go and read the paper, it'll make more sense. But the data one, I feel, is the easiest to handle in the pre-processing. The other one is check for bias as often as possible, using any metric that is applicable. And so, once your model has been deployed and people have started using it, even then, it is very important, just like you would check for accuracy on an ongoing basis. And by the way, I'm using accuracy as a loose term. So you should with bias, right? If you've tried to mitigate bias and your data or your model has been deployed, depending on what new data it is seeing, you absolutely should run your bias detection checking as often as possible. And the last thing, it's also important to understand that AI Fairness 360, it's an open source toolkit. Right now, it works with some well-defined data sets and some well-defined use cases, and the documentation has a list of what these are. And so it is by no means a magic bullet. I think it's a great starting point, and it tells you where to look. It's almost like it's a torch, and it'll shine the light in the right direction and tell you, hey, there's a clue there, go look there. But it's not going to give you a perfect model at the end of it that here you go, all your problems have been solved. But it's a start. Here, let me check for questions. No questions. Is anybody listening? Oh, yes, the demo part now, right? So I've been talking for a while now. Let's look at the demo. So let me exit this PowerPoint show. So first of all, here's the GitHub repo that I was talking about. So the replay is from an earlier webinar I did, but the slides are here, as well as everything about AI Fairness 360 that I think is important to know, as well as some of the links from the slides. This, by the way, talk from an MIT grad student on TED. It's a TED Talk. It's very interesting on facial recognition if you have a desire to learn more about that. IBM recently, I think we made an announcement last year we're getting out of the facial recognition business altogether, which was great. And then I've listed all the papers here. I'm going to go back here and link them to the right PDF so it's easier for you to find it. OK, let me paste this in the chat somewhere so you can get it somehow. OK. All right, and then moving forward, here's the first paper. This is kind of tricky, This is Arvind Narayanan, the Princeton University. I don't know if he's a professor or I guess computer scientist, and he gave the talk on 21 metrics and biases, and it was a fantastic talk. But but I couldn't find the paper. So what I've done is in this GitHub, I've linked to his YouTube video. And again, take a look at that. It's a nice scientific talk, but also it's a little bit philosophical. What he's trying to do is he's trying to convert the 21 metrics into English, into layman's terms, so people can understand. And that was the first talk I saw when I started to get into this topic, and it was very, very amazing. Here is the AI Fairness 360 sort of homepage. Let me put this here. So here, this is the homepage for AI Fairness 360. As you can see, there's a web demo. We'll go through that. There's this paper here is by IBM describing the toolkit itself. So it's a good read. There's a bunch of tutorials. Tutorials are normally in the form of Jupyter notebooks that you can import. Hopefully they're doing some R tutorials as well. I'll ask the team. And then there's also a question I see people are asking. Somebody's asking which industries is this used more in, right? So I feel financial industries, definitely, that's a big, anywhere that the impact is more, right? Going back to how does this model impact you? I think financially or in healthcare, that's where people really can relate, right? So those are two industries that even IBM has big use cases. I'll try and get a better answer to that question. I can talk to the team and see it and ask, hey, what clients do we work with in what space the most? But from the different sources I've seen, it's the financial industry, especially using computers. It's such an intrinsic part of Wall Street and finance and banks that I think their exposure to this as well as adoption to this is very fast. Especially now with the time of social media and Twitter and whatnot, like you saw with the Steve Wozniak tweet. It's things like this blow up really fast, which for the better. I think it should be that way. Here's the different mitigation algorithms, right? So we talked about reweighing a little bit, and this is kind of cool. The link will actually take you to the source code. So if I open this in a new tab, it takes me to the Python file that's implemented reweighing. So you can actually go in here and see what's going on, but also it links you to this paper that explains what reweighing is. Actually, I was reading it, like I said before, so I have it here. And if you read through this, I was thinking we can probably do a webinar on each paper and call some very smart researchers from IBM and academia to come talk to us. That might make for a really good webinar. But yeah, you can read through all of the papers behind these algorithms, look at the code if you want to. But what I want to show you now is, by the way, here's the different different metrics, and they also link to the code. So if you want to actually see how this metric was implemented, right? So all of this is coming from this classification metric, a subclass of the binary label dataset metric, and it defines the actual metric, and you can see how they come up with looking at the data, how they determine the predictive parity versus the other ones. So a lot of transparency. Okay, so let's do a demo. So they've built this sample demo page for us to learn more about different kinds of metrics. So there are 3 different data sets here. Let me increase the font a little bit. And let's look at the last one, which is the adult census income. And this, let's look at this, adult, how do you spell census? Okay, sorry. Adult census data, I think this is part of the UCI data set, if I'm not mistaken. So it's this one here, UCI machine learning repo. And you can see the different attributes, right? So what we're trying to do here is based on these different metrics, right? So age, maybe a protected variable, work class, which is what kind of work you do. I'm not sure what this is, but there's some easier ones to understand. Your marital status, your occupation, race, sex, So these are definitely need to look at these to see if there's any bias based on these protective attributes. And there may be others too, right? Like these are the typical ones, and so that's why I'm pointing them out. And your country of native country, your country of origin, that might also play a role. I don't know. Okay, based on all of this, we have a labeled data set that's telling us if this individual's salary is more than 50,000 or less than 50,000. So that's our target class, right? That's what we're trying to predict. So let's go back to our demo, and yes, I want to pick that. And as you can see at the bottom here, it's saying this demo is using race as a protected attribute, where white, value of white is privileged and a value of non-white is unprivileged group. And then it's using sex as a the second protected attribute, where the privileged class is again, the privileged value is again male, unprivileged class is female. Okay, so I guess it's saying like if there's a bias against non-white people and female or women when predicting these salaries. Oh, I guess I could have just clicked on this learn more to go to the data set. Okay, good to know. All right, so let's look at that. So I click on next. It's running the metrics against the data itself to see if there's any bias present in the data. Now, one thing to note is the accuracy at this point, with no mitigation applied, I forget what exact algorithm it's using. I think I told the team that might be useful information to put here, maybe. But the accuracy is around 82%. And it's saying it's looking for these different kinds of metrics. You know, we saw some of these before. Also, you can click on this little information icon to see what the definition of this metric is. In case of any sort of difference, we want to get as close to 0 as possible. So we know, there is a 17% bias towards the unprivileged class, which in this case happens to be non-white, using race as a protected attribute. Whereas the equal opportunity difference is not showing a big bias. If you look at disparate impact, which is, again, it's just a ratio, same as statistical parity impact, so obviously there is some bias there as well. And then the second thing is looking at sex as a protected attribute, and it seems like the bias is showing up in a lot more metrics than it was showing up when we looked at race as the protected attribute. So okay, so once we have detected there is some kind of bias using the toolkit framework, then we can click on next and go into mitigation algorithms. So again, in pre-processing, there's a bunch of algorithms here, right? So reweighing is one. Also optimized pre-processing. They work on data. Then there is a debiasing algorithm that's working on the model itself. And then there's finally another mitigation algorithm that's working on predictions. And again, the actual algorithms are sort of out of scope for today. But let's try reweighing, since that's the easiest one to understand. So if I click on that and say next, and now it's actually applying the mitigation algorithm or model, and then it'll do another check on accuracy to see what happened. So in this case, after the reweighing algorithm was applied, as you can see here, it's able to reduce the parity difference as well as the disparate impact. For any kind of ratio, you want it to be as close to 1 as possible, and differences as close to 0 as possible. So it's done fairly well, but my accuracy has gone from 82% to 81% using the same model, right? Because remember, this is applying the mitigation technique to the data itself, even before touching the model. And same thing with when using sex as a protected attribute between male and female, it's able to reduce the bias by quite a bit by using these different mitigation algorithms. Right, so there's a question, how well does the performance of a biased mitigated model hold up over time compared to an unmitigated model? So that's a really good question, right? And again, as I was saying, this is something you have to check on an ongoing basis, even after you've deployed your model. Generally, there's a conflict with bias and accuracy. When you say performance, I'm guessing you mean accuracy of the model. So yeah, there's definitely a tug of war going on there. I'm trying to understand the question. So when you're deploying a machine learning model, again, we have something called OpenScale. That's it's a solution that sort of keeps a tab on the model, and as new data comes in, it checks the accuracy, and if it goes down, it'll go retrain the data, retrain with the new data, come back and see the performance. So I guess the point I'm trying to make is, as you're checking the performance, you also have to check for bias, and bias may be introduced way after your model has been deployed, right? It doesn't mean if your model didn't have any bias when it was deployed, if some new data comes in that it's never seen before, that may be a candidate for bias as well. I don't think performance of a bias mitigated model hold up over time compared to unmitigated model. Yeah, I think I understand your question. I want to say that's a good question. Let me get back to you. Maybe I'll put because I have an answer in my mind, but I want to actually get a more detailed answer from the researchers who work on the open source project. So let me confirm my answer with them and get back to you. I'll probably put something on the Meetup group, Rebecca. Thank you. Actually, that brings me to another important point. So if you go to the community section here, there is a Slack community for AI Fairness 360, and this community is where all of the researchers hang around to answer any questions, and also they have special channels to discuss specific algorithms and models. So this is where I was going to ask to get a better answer than what I have, but feel free to go there as well and join this community if you're interested in this topic and bias in general. Okay. And then the other thing I want to show you is that was the demo. If you go to resources and tutorials, you'll see it'll take you to the GitHub repo that has the Jupyter notebooks to be able to, like this demo site was just built for us to test things out. But behind the scenes, this is using the Python framework to do the bias detection. So in here, there are different demos. There are different demos in terms of Python notebooks. And if I look at the reveighing one, so if I look at the reveighing one, this is what we just did. So let me increase this a little bit. This is what we just did with the click-through demo that I was showing. So in this case, it's importing a whole bunch of packages from AI Fairness 360 library. So you can see different kinds of data sets that it'll use. This adult data set is what we just used. There's the Compass and the credit card data set. And then from metrics, it's now getting the classification metrics from this, or it's getting the class from this package, as well as the reveighing library. So if you go down, it's using logistic regression to actually do the modeling itself. This first cell, it's just setting things up, right? So in this case, it's saying use the adult income data set. And as you go down here, it's doing some very basic analysis of what's inside the data set. One thing you have to realize is with the AI Fairness 360 toolkit, at least, you have to tell it what the protected classes are, and you have to tell it what the privileged group and the unprivileged group is. And then you can find, you can use the metric data set as is being shown here, as well as the reveighing algorithm. So very easy to import and run this notebook, but it'll come back with, let's see. Somewhere in here, it's going to show you the result of reveighing. All right, so I guess this is one of the charts that shows that, right? So it's got the accuracy versus the disparate impact, and it's showing you, which is our bias metric, and it's showing you the inverse relation between the two. And then this is where you have to pick your best threshold in order to maintain a high enough accuracy that is valid for you, yet bringing down the the bias. All right, so this is one of the notebooks, and then of course there are the other ones as well. In terms of what's exciting to me, it's actually the for me, it's not even like, there's the research bit of it, which is the metrics themselves, or the research that's going on post-processing or in processing. That's all very cool, and I love to read the papers and try and get a deeper understanding of what's going on. But for me, I don't think the awareness that is being generated right now, based on what is happening around the world, in this country, I think that is amazing, and it's headed in the right direction, and hopefully it will continue to do so. And what's exciting for me is the part that we can play as data scientists, as computer engineers, as software engineers, in asking the right question, right? So next time you go to next time somebody produces a model, you should be asking these questions. You should be asking, hey, did you ever detect for bias in the data? Where is the data coming from? Who are the different stakeholders that are looking at this product to make decisions? What kind of decisions are being made? Think about and debate on who could be the privileged group and unprivileged group in this case. And so all of that to me is very exciting, that making a toolkit like this available to us as data scientists, and making it so easy to be able to use this and at least start having a discussion. We may not have all the answers, but at least start having these discussions is very important. All right, I think I've spoken for an hour now, and I'm boring the heck out of some people, I'm sure. So I'm going to stop here. Again, please share the link with everybody so you have all of these resources. I'm on Twitter, as I said. Let me bring it up. Here, if you want to have a discussion on this is me, this guy. So if you want to have a discussion on any of this, I'm more than happy to talk to you and, make the most of quarantine by getting on a Zoom call and having an interesting chat. So with that, I think I'll hand it back to you.
Yeah.
Thank you.
Hey, thank you so much for the talk. It's very interesting. And I feel like it's also very relevant to whatever is going on right now in the world. Yeah, and again, thank you everyone for listening in. Remember to join our meetup. It's Data Council NYC. And reach out to us if there are other talks you're interested in listening to and any topics. And again, thank you so much. Have a good evening.
Thank you for having me. Bye-bye.